All right, today what we're going to be looking at is a new question, well, not really a new question, but new to us question about rules for differentiation. And the rule that we want to look at here, or what we want to determine is, let's suppose that we are given f and g functions with derivatives f prime and g prime, and we want to know what is the derivative of f of x times g of x. This is a pretty important question. Can we figure out what happens if you take the product of two functions? What does that do to the derivative? And the resulting rule is known here as the Leibniz Rule. So he was German, the EI in German makes an I sound, so Leibniz. And he and Newton are kind of credited with most of the sort of formal initial development of calculus, even though other people had done a lot of stuff involving tangent lines before them. They're kind of still the ones who get most of the credit for really putting calculus into its more or less fully developed form, although again, they didn't really have the formal definition of a limit. They did a lot of things using more intuitive arguments rather than rigorous arguments. But anyway, this rule is named after him. Now, interestingly, the story goes that he actually got this wrong when he first tried to figure this out and didn't realize it was wrong until the next day, and then he figured out what it really should be. So I want to mention the mistake, okay? And this is because it's something that a lot of people might guess the answer to be. And I want to just kind of illustrate how even very smart people can get that kind of thing wrong. Well, some people might guess that it would be the derivative of f times the derivative of g. I mean, that would be kind of nice, right? If the derivative of a product is the product of derivatives. Unfortunately, no, this is not correct. And it's actually very easy to see this cannot be right. Why? Well, just consider f of x equals 1, g of x being equal to x. Then f of x times g of x should be equal to x, because multiplying by 1 doesn't change anything, which is still g of x. And that means the derivative of f times g should still be the same as the derivative of g. But if we take the product of the derivatives, what we get here is f prime of x equals 0, g prime of x is equal to 1. Their product, f prime times g prime, is equal to 0, and the derivative of g, the derivative of x, which is the same as g, of course, is equal to 1. Okay, so we end up, this is clearly not correct. This would give us the wrong answer if we try to apply it in this case. And therefore, this rule cannot be true in general. So this is incorrect. However, there is a nice way to reason through what is going on here. And the way that we're going to figure this out is I'm going to think about the derivative using a slightly different notation than what we have used before. So we're going to use the notation delta f. This is going to be equal to f of x plus h minus f of x. In other words, it is the change in the function f. And if I do this, and if we write delta x in place of h, because it's convenient to use delta x here, then we can say that the derivative of f with respect to x is the limit as delta x goes to 0 of the change in f divided by the change in x. I've actually kind of mentioned this before. It's sort of where this df by dx notation comes from. Okay, but why is this nice in this case? Well, let's think about the derivative of f times g. this would be equal to the change in f times g divided by the change in x. So what is the change in f times g? Well, here is one way to write out the change in f times g. It's going to be f plus the change in f times g plus the change in g minus f times g. Because if you think about it, how much does a product change? Well, you can't just, it doesn't change. It's not just the product of the changes. If two quantities change, then their product actually changes by this amount. Think about how much does f change, multiply, like this is the new value of f times the new value of g minus the original value of f times the original value of g. That's probably the easiest way to sort of think about where this is coming from. I'm sorry, I forgot my limits here. Limit as delta x goes to 0 and limit delta x goes to 0. And of course, this is still being divided by delta x. So what happens when I expand this product is very interesting because I have to expand this using the rules for expanding binomial products. So what I'm going to get is I'm going to get f times g plus delta f times g plus f times delta g plus delta f times delta g minus f times g, all divided by the change in x. Now this seems rather annoying and confusing, but there's actually a very nice geometric way of understanding this. If we think about a rectangle whose one side is length f and whose other side is length g, if I change f by a little delta f, and if I change g by a little delta g, then the total change in f times g is going to be this whole region, which requires me to take delta f times g, delta g times f, and delta f times delta g, right? So we actually have these three new regions, so to speak, that come into play here. And really, all we're doing here is this is just a geometric way of understanding what happens when we do this product. So at this point, what I can notice is that f times g minus f times g, those are both going to cancel. So what do I have left? Well, I can break up this fraction into a few pieces. I have the limit as delta x goes to 0, and then we're going to have g times delta f over delta x, and let's put this all in parentheses, plus f times delta g over delta x, plus delta g times delta f over delta x. But in the limit as delta x goes to 0, delta f over delta x, this is going to become f prime. Delta g over delta x, what is that? It's going to be g prime, right? And delta f over delta x, once again, well, this is going to be another f prime. Also, as delta x goes to 0, delta g goes to 0. Why? We said that these are differentiable functions. We were given f prime and g prime, so we're assuming their derivatives exist. Because their derivatives exist, they have to be continuous, and that means that the change in g is going to have to be going to 0. So, what we end up with in the limit is the first term becomes g times f prime, and the second term becomes f times g prime, and the third term becomes 0 times f prime. And I can rewrite this as f prime g plus f g prime. And there we go. This is going to be our Leibniz rule or product rule. So you can use either name for this particular rule. Now, you might wonder, can we do this argument using the original kind of notation that we do for derivatives? The answer is absolutely. We can, it's just not quite so intuitively obvious what's going on. So that's why I wanted to show you how to do it this way first. If I wanted to do the limit as h goes to 0 of f of x plus h, g of x plus h minus f of x, g of x, divided by h, what I'm going to do is I'm going to add and subtract a certain quantity in the denominator. So I'm going to take this, and here's my f of x plus h times g of x plus h. I am going to subtract f of x times g of x plus h. That means I also have to add f of x times g of x plus h. And then, of course, we are subtracting f of x, g of x. Okay, I am really running out of room here. Can we make this a bit more efficient in space? Let's try that one more time. We have f of x plus h, g of x plus h. Now I'm subtracting f of x times g of x plus h. That means I have to add f of x times g of x plus h, and then I am still subtracting f of x, g of x. Okay, so now what I can do is I can break this apart into these two fractions, because from the first two terms I can factor out a g of x plus h. From the second two terms I can factor out an f of x. So I can rewrite this as the limit as h goes to 0 of g of x plus h times f of x plus h minus f of x divided by h. And then we're going to have plus f of x times g of x plus h minus g of x divided by h. So I've split this into two separate fractions, and I factored on each of those fractions. So I split it up into two halves right along here, and I then just factored things to get to this step. But now what we notice is that this here is going to become f prime, this here is going to become g prime, this is going to become g, and this is still just f. So we get exactly the same thing as we did before. The downside here is that, to my mind, this trick of subtracting and adding something in the numerator isn't really as obvious as if we work it out using the other form. So I think it's better to kind of look at the other form. That gives us a very intuitive, clear understanding of why this rule works the way it does. Whereas if we just kind of do this trick, then it seems like it falls out of nowhere. And I don't like things that seem like they fall out of nowhere. I mean, sometimes we have to use them, but it's always nice if you can understand, if you can get a real intuitive notion of what is going on here. So there we go. We have got this whole rule worked out for us. Now, like I said, I mean, Leibniz, the first time around, he apparently didn't get it right on his first try. And then he realized he'd made a mistake. And this is something that I actually, just as a momentary aside about mathematics and working in mathematics. A really famous mathematician, Benson Farb, said that mathematicians spend 90% of our time failing. And somebody said to him, wow, you succeed 10% of the time? And he said, no, that was a vast overestimate. The truth is that when we're working on stuff, when we're doing new research and things, we're basically spending 99% of our time messing up. And so when you make mistakes in math, like, I'm not telling you this to say, oh my God, math is so difficult or something like this. I'm telling you this because if you make a mistake in mathematics, that's normal. Nobody just does math perfectly, okay? We all, at some point, struggle with what it is that we're trying to figure out. And the difference in a lot of ways, I mean, of course, the very great mathematicians, they were very smart people, but it was also that they didn't let themselves get bothered if they were messing things up. They didn't let themselves get bothered if they made mistakes, okay? So they kept going. Another example, right? Einstein spent 10 years between when he published his paper on special relativity and when he generalized it to general relativity. Well, it's not like he was just sitting around for 10 years and then said, oh yeah, here's general relativity. He spent 10 years screwing up general relativity before he got it right. Okay, so persistence is really the key in mathematics. Persistence and optimism, and not letting yourself get panicked if you feel like you're making a mistake somewhere. So it can feel like you're not getting anywhere. The truth is, you are learning at least one way that doesn't work. So, when Leibniz made that mistake, it wasn't simply, oh, this is a mistake. It was, no, I figured out a way that doesn't work, and this helps you to think about, okay, what do I need to go back and check to see what would work? Now, let's go ahead and look at some examples of using the product rule. So one example of using the product rule that we can say right away is going to be, what if I wanted to take something like the derivative of x squared e to the x? We know how to take the derivative of x squared, and we know how to take the derivative of e to the x from what we said in our previous couple of lectures, but this product is something that we don't know how to do, and frankly, if I were to plug this into the original definition of the derivative, this would be a nightmare. Well, we could probably do it, but it would be a really, really tricky thing to actually write down this limit and simplify it and come up with, using the limit of the difference quotient. It would be very annoying. Using the product rule, all I need to do is to break this up into an f and a g, and then I can say, well, f prime here is going to be 2x, g prime here is going to still be e to the x, and then I just have to write down f prime g plus fg prime. And this is going to be 2x e to the x plus x squared e to the x, which is going to be, if I factor in e to the x, I get 2x plus x squared e to the x. So there we go. A nice little example of using the product rule. Of course, we can do things that are more complicated as well. So for instance, we can have something where maybe we have to take the derivative of 2x cubed minus x e to the x plus 4x. So in this case, we need to actually break this up into two different derivatives, okay? So what I'm going to do is I'm going to break this up into the derivative of 2x cubed minus x e to the x plus the derivative of 4x. And the reason I'm going to do that is because we can handle each separate term separately. That's one of the nice properties of the derivative, right? We said that you can split the derivative over sums and differences. And now what I can do is, in this first problem, I can think of this as my f and this is my g. And I can say, okay, then my f prime is going to be equal to 6x squared minus 1. G prime is going to be e to the x. So this is going to be 6x squared minus 1 e to the x plus 2x cubed minus x e to the x. And then the derivative of 4x is going to just be 4. And finally, I can factor the e to the x here and say, so this becomes 2x cubed plus 6x squared minus x minus 1 e to the x plus 4. Now, once again, observe how straightforward this is compared to trying to use the limit of a difference quotient. If I tried to do a limit of a difference quotient with this thing, it would take me like an hour to work through the entire thing. In fact, frankly, I don't even know how I would end up figuring this out. I'm sure we could do it eventually, but it's not something that is obvious to me how I would even simplify. But by appealing to these rules for derivatives, we are able to calculate this without ever having to explicitly calculate a limit of a difference quotient. So you can see how much this really saves us a lot of time and effort here. Now I want to mention something else about the product rule, by the way. You remember how we proved the power rule for natural numbers we said that the derivative of x to the n is nx to the n minus 1. We did this using the binomial theorem and the difference quotient. Well, you can actually prove this using the product rule in the following way. And I'm going to show you this because it's a very interesting kind of proof. It's what we call a proof by induction. So we say, in this case, for n equals 1, the derivative of x is equal to 1. We just have to calculate that directly. And then we say, okay, let's calculate the derivative of x to the n plus 1. Well, this is actually the derivative of x times x to the n, which is equal, if this is my f and this is my g, this is going to be equal to x to the n times the derivative of x plus x times the derivative of x to the n plus 1. I'm sorry, x to the n. There we go. So this is then going to be x to the n plus x times whatever the derivative of x to the n is. But now, suppose that we know that the derivative of x to the n is nx to the n minus 1, then this is going to become x to the n plus nx n to the n minus 1, which I have run out of room here. This is going to become n plus 1 x to the n. So what we've established is that if this formula is true at the level of n, it is also true at the level of n plus 1. And it is true when n is equal to 1. Therefore, it must be true when n is equal to 2. And therefore, it must be true when n is equal to 3. And so on. This is called an induction proof. We prove something is true at level 1, and then we prove that if it's true at level n, it's true at n plus 1. Therefore, it has to be true for all natural numbers. So we already knew this result, again, by using the binomial theorem. But if you didn't want to use the binomial theorem, you can prove this result by just using the product rule. You can also use this to figure out what is, for P and Q, natural numbers. You can use this to calculate the derivative of x to the p over q. Why? Because, well, this is going to be equal to the derivative of, how do I want to write this down? Okay, so here's the way that I want to do this. What I want to do is I want to think about the derivative of x to the p over q raised to the qth power. And I want to think about this in two ways. On the one hand, this is the derivative of x to the p, which is going to be p x to the p minus 1. But on the other hand, this is going to be a product of q copies of x to the p over q. Now, what happens when you apply the product rule to this whole thing? Whoops, that's not p of them, that's supposed to be q of them. What happens when you apply the product rule to something like this? Well, what you're going to end up getting is you split this thing up, because one of the things that you can do with the product rule is you can generalize it. So you can say, and if you think about this for a moment, like the derivative of f times g times h is just going to be f prime gh plus f g prime h plus f g h prime. And if we kept on going up with the numbers, we would get exactly the same thing. So if each of these functions is the same, each one of them is x to the p over q, what we're going to get is q times x to the p over q times q minus 1 times the derivative of x to the p over q. And then what we can do is we can say, okay, but these derivatives have got to be equal to one another, and therefore this must be equal to p times x to the p minus 1. And now just divide both sides of the equation by q, x to the p over q times q minus 1. And what you will end up with here is going to give you exactly what we said. You end up just multiplying by p over q, and you reduce the exponent by 1. So this allows us to establish that the power rule is going to be valid even for rational exponents, at least when they are positive. Now, how do we do the negative case? Well, that brings us to the next rule that we want to do, and we'll see later how this applies to getting the power rule for rational negative exponents. But how do we do this for, how would we deal with the negatives? Well, one of the things we want to do now is we want to ask, what if I wanted to take the derivative of f divided by g? Well, this has a more complicated derivation, and I think I'm not going to bother going through the derivation of this particular rule. It's not awful, but it's not especially enlightening. I mean, I guess we can kind of figure it out. So we can say, well, this is going to be the limit as delta x goes to 0 of f plus delta f divided by g plus delta g minus f over g, all divided by delta x. Now, if I take a common denominator here in the numerator, limit as delta x goes to 0, we're going to have fg plus g times delta f minus fg minus f delta g, all divided by g times g plus delta g, all divided by delta x. Okay, this is beginning to become a little bit of a mess. Much messier than our product rule case, but you'll notice that I haven't really done anything like weird. All I've done is I've taken a common denominator, combined my fractions. So let's continue rewriting this a bit. Limit as delta x goes to 0. Now, I am going to take, just for the moment, for the sake of convenience, I'm going to bring 1 over g times g plus delta g out front. And then inside, my fg's cancel, and I'm going to have g delta f over delta x minus f delta g over delta x. Okay, I've lost a parenthesis. My apologies. Now, why did I want to do this? Why did I want to factor things this way? Well, the reason is because as delta x goes to 0, this is just going to become f prime, this is going to become g prime, and this is going to become g squared. So, what we end up with is gf prime minus fg prime divided by g squared. And this is known as the quotient rule. So if you wanted to deal with the negative exponents now on x, you can just use the quotient rule. And you can say, well, x to a negative power is really 1 over x to a positive power, and then you apply the quotient rule. And I will leave it as a little exercise for you to see how, now that we know the power rule for positive x and for rational positive x's, for positive integers and positive rational x, use the quotient rule to see that the power rule is actually true for negative exponents as well. Now, that still doesn't establish the power rule for irrational values of x. We will see how to do that later. Remember, and the way that we're going to do it is actually really cool. We're going to use the results that we have for exponentials. Well, the thing is, to prove what the derivative of the exponential is, all I needed was the power rule for the rational exponents. That was the reason why, if you remember in the previous lecture, when I took a certain derivative, I said we're going to restrict ourselves to the case where these exponents are rational. That's because to see what the derivative, to see that the power rule is true for irrationals, we actually are going to use a clever trick involving exponentials. But we'll get to that later. This is sort of my teaser for our future stuff. So let's take a quick look now at some examples of using the quotient rule. Let's suppose that I wanted to take the derivative of x squared minus 3x divided by 5x plus 2. Now, again, I could try plugging this into a difference quotient, but it would be a mess. A real mess. And so instead, I'm going to just use these rules. Well, I'm going to say my f here is equal to x squared minus 3x. G is 5x plus 2. That makes f prime into 2x minus 3 and g prime into 5. And this means if I do g times f prime, this is going to be 5 times 2x minus 3. Then we do f times g prime. So that's going to be, why did I do 5? I'm sorry, 5x plus 2. There we go. G times f prime minus f prime, which is 2x minus 3, times g prime. What? Let me start this over. Holy crap, I have really managed to make quite the mess of this. Okay, g times f prime, that is going to be 5x plus 2 times 2x minus 3. There we go. That is set. Now we have f subtracted, that's x squared minus 3x times g prime, which is 5. Goodness. And then on the bottom, we're going to have 5x plus 2 squared, because we have g squared. And now it's just a matter of simplifying this out, right? So at this point, all of our actual calculus stuff is done. It's just an algebra simplification problem. So this is going to become 10x squared, and then we're going to have minus 15 plus 4, so minus 11x minus 6, and then we're going to have minus 5x squared plus 15x. And in the bottom, we have 25x squared plus 20x plus 4. And so this is going to become 5x squared plus 4x minus 6 divided by 25x squared plus 20x plus 4. Let me just make sure I did this correctly. 2 times 5, that's 10, and then another, yeah, okay, we're good. So we've combined everything together and simplified it down, and there is our derivative. Again, if you want to see why these rules matter so much, I invite you to take this, do a difference quotient, and take the limit. And after you have either figured that out or given up on it, I think you will very much see, if it's not obvious already, why having these rules is so really convenient for us. And of course, we can do this combined with our stuff for exponentials as well. So here's an example that I want you to take a moment to think about. What would be the derivative of x divided by e to the x? Take a moment to try to figure this out, then come back, unpause this, and we'll work it together. All right. So I'm going to take f to be equal to x and g to be equal to e to the x. That makes f prime into 1, and it makes g prime into e to the x. So we are going to have g times f prime, that's going to be e to the x times 1, minus f times g prime, that's going to be x e to the x, divided by e to the x squared, which is really e to the 2x. And I can factor out an e to the x, so this becomes e to the x times 1 minus x divided by e to the 2x. The e to the x is partly canceled, so I end up with 1 minus x divided by e to the, whoops, not 2x, just e to the x. So there we go. We've managed to figure out this derivative in a fairly straightforward manner, honestly, considering how difficult this would be if we plugged it into a difference quotient. So that covers our product and quotient rules. Now, I want to mention one more thing about derivatives, which the textbook actually went over a bit earlier, but I think it's better to do it here because now we actually have some rules that make it easy to take derivatives. I want to talk about higher order derivatives. So once I take one derivative of a function, I get a new function. Well, I could take a derivative of that new function, and that would be the second derivative. So we have the second derivative. This is going to be the derivative of f. And we also write this as d squared by dx squared f. We can also write this by putting 2 primes instead of 1, if you like the prime notation, which I do. The third derivative is now going to be the derivative of the second derivative. And we can write this as d cubed by dx cubed of f, or we can write this with 3 primes. And in general, you keep on going like this. So if you take n derivatives, this is the nth derivative, and it can be written as d to the n by dx to the n f. Instead of using primes, if you go with more than 3, you just put the n in parentheses up here. We use parentheses to make sure it's clear this isn't an exponent. But if you put the n in parentheses, that means you take n derivatives of this thing. So doing this kind of thing is fairly straightforward now that we have our rules. If I have, for example, f of x is equal to 3x squared minus 5x plus 2, then the first derivative is going to be equal to 6x minus 5, and the second derivative is just going to be equal to 6, okay? So, and you can keep on going. Like maybe you have to use the product rules at some places, maybe you have to use the quotient rules, but whatever you're doing, you just keep on using those rules and you repeat this procedure however many times you need to get to the derivative you want. So there we go. Just another little note here. And later on, we will see what is the geometric significance of these higher order derivatives. So it does turn out that these higher order derivatives contain a lot of information about the original function. So they are going to be very important later. But for now, just know that this is what we call them. This is how you calculate them. They're not really anything new. It's just that you repeat the same calculation process over and over again. All right, so what we'll be starting in on next is we will see how to take derivatives of trigonometric functions, and then we will see how do you take derivatives of functions that are composed together. Because so far, we've seen how to deal with derivatives through all of the arithmetic stuff. Addition and subtraction we already handled. We did products and quotients today. The last way that you can really combine functions is through composition. Well, I guess you can also exponentiate functions, but we'll deal with that later. So the next thing we're going to deal with is what happens when you compose functions. But first, in order to give ourselves more functions to play with, we're going to see how to take derivatives of sines and cosines and the other trig functions then using these rules. So that's what we'll be dealing with next week.